Uh,
They hired you and fired you.
yeah, pretty much. They can do that to part-time instructors. Yeah. Well, I'm not fired. I just don't have a position for fall right now. Yeah, I guess. But it's fine with me, is let me spend more time with my family, so that's cool. So here's everything we're doing. And we're gonna do this by collecting some data, 2 variable data. Okay, so I want some information from you, and if you saw on the syllabus, I called today stinky feet. I get a ruler and I measure your shoe or your foot, right? So you take your shoes off and I measure your foot and measure your height. Is there a correlation? Okay, so this word correlation right here, correlation, are they related? Are 2 variables in the word correlation, are 2 variables related? The stronger the relationship, the better. Well, I'm not going to ask you to take your shoes off because my feet stink. I don't know about yours. But just say that. But I'll just get your shoe size. Not everybody wears the right size shoe. That could cause back problems. I know that. I know my daughter, she wears flat bottom shoes, and she's like, I have back problems and I got knee problems. And I took her to a foot doctor, a podiatrist, and the doctor's like, well, just get inserts for your shoes. All your shoes are flat, and flip flops are the thing, especially for women, all this, the shoes are terrible. They're not designed to walk in, especially if you're on your feet all day with your job. You want shoes that fit well and have good support for your foot, right? So you don't want to wear those flat shoes or the Crocs or whatever you're going to wear. Unless the Crocs have support, of course. So those things cause back problems. It's known. Statistical studies have been done. But we want to know how related are these 2 variables, your shoe size and your height. We're not going to separate males and females because we don't have enough people. So we're just going to put everybody together. And we're going to do all these things with this information. And that's pretty much everything that you need to know for chapter 9. Sound good? So let's collect data. So we're just going to go around the room. And if you're online, just type in the chat box your shoe size and your height. If you don't know your height, then just take a good guess or go get your tape measure to measure yourself. So we got our shoe size and our height is going to be in inches. Again, this is one variable. Height is going to be measured in inches. We're not going to measure in feet because then we'll be like, oh, you're 5 feet, you're 6 feet. Okay, so we want inches. Like 5'9" is 69 inches. 5 feet tall is 60 inches. So if you're about 5 feet tall, if you're a little under 60, 59. Right. So we're just going to go around the room. Let's start over here and we'll go this way. And one thing, don't be embarrassed about your shoe size or your height. There's no big deal. Okay, we're adults, we're mature, right? I wear size 7.5 and I'm 54 inches tall. You can laugh all you want. All right. Crowd goes wild. Oh, they're chiming in. So here we go. Start over here.
8 for shoe size, and then I'm 5'2", so I don't know.
5'2"?
Yeah.
62.
Oh, 9.5 and 5'7". So that's
Oh, that's me. 6.5, 60 inches. 9.5, 64.
Size 10 and 69 inches.
Size 6 and 59 inches. 6.5, 64. 6.5, 60 inches. 8.5 and 5.
Carry over here. We're back.
9 and 65 inches.
6.5 and 65 inches.
9 and 65.
Glass.
I'm 4'11", and when she said you was right.
And shoe size?
5.
5, okay. And let's check our online people. We got a couple. 8.5. And 59. And 7 and 3. 661. 661, 1664. Seven and 63. Right over here, 7 and 63. And the other one was 7 and 7.5 and 63. Okay, so the next thing we're gonna do, okay, we have 2 variable data. We could explain what's going on with this data. These numbers are quantitative. Okay, they're numbers. Does that make sense? Remember quantitative and qualitative data? We have quantitative data. We can say there's a correlation. If we have qualitative data, if we're counting, like, do you wear glasses? We count how many people wear glasses. Oh, there's 8 people wearing glasses and 20 people not wearing glasses. That's counting. That's qualitative data. Do you wear glasses is a yes, no question. That's not a number. Okay, so it's really important to understand that if you have quantitative data, you would describe this data as being a correlation. If you have qualitative data, you would describe the data as an association. Is there an association between wearing glasses and how tall you are? Okay, that doesn't make any sense at all. Your height has nothing to do with wearing glasses or not, right? Your height might have something to do with back pain, but we can't say there's correlation. Do you have back pain? That's a yes, no question. That's qualitative data. So we'd have to use the word association. Am I making sense with that? Qualitative, association, quantitative, correlation. So some people, a lot of people actually, in fact, and you might see this, you guys don't need to write all that information down, because we're gonna make a scatter plot, okay? If you're writing it all down, you're wasting your time, okay? We're gonna make a scatter plot by hand, okay? But a lot of people that, especially I hear this on the news, when I used to watch the news, and I taught statistics, it's my 16th year teaching this class. I watched the news and there was like, there's a correlation between gender and how much food you eat at a buffet, right? Gender is qualitative, right? So you can't use the word correlation. There's a correlation between the color of your car and getting a speeding ticket. Both those variables are qualitative, but I hear the word correlation all the time. People use the word correlation incorrectly, especially people that think they're smart. All right, so I just want to point that out with this statistical thing that you might run into. Yes.
I never understood the saying correlation does not equal causation. Are we gonna go over what exactly that means, or?
Okay, so yeah, I could explain it real quick. He said, and there's a saying is correlation. The correlation does not equal causation. So if 2 variables are related, that does not mean cause and effect. So there's a correlation between the amount of alcohol consumed in Santa Maria and the number of gang members in Santa Maria. Does that mean all the gang members are drinking alcohol? Okay, not necessarily. There could be other factors. They're called lurking variables. Okay, or in the this one I think is in the book, the late 1800s in New England, right? New England, when the states were being founded, there's a correlation between the number of ministers and the amount of rum being imported. There's a 0.999 correlation. Does that mean all the ministers that came to the United States were drinking all the rum? right? When you think of rum, you think of pirates and stuff like that, right? Not ministers that are building churches. Well, what is the lurking variable? It's population, right? There's more people that live in the city. So if there's more people that live in the city, then there's gonna be more people consuming alcohol, right? Of course, there's gonna be more gang members living in San Marin than there are in Los Alamos, right? So there's the population, there's gonna be more crime, there's gonna be more businesses, there's gonna be more things happening. Population, bigger city has bigger problems. So, those things happen. So when you use the word correlation, does not mean causation. There's not a cause and effect. One thing did not cause another. That's used a lot in experiments also. So if you set up an experiment and you try to link two variables, with a cause and effect, and there's correlation between the two variables, like, oh, these two variables look like they're linked. That doesn't mean that one thing causes, or one thing is caused or affected by another. Okay. Did that make sense? Did I answer your question? I hope. Yeah. But we'll get to that when we set up the scatter plot. So let's make the scatter plot. This is X. This is Y. So when we do conduct our research here, we want to know if X causes Y, cause and effect. Well, not necessarily that, but does X predict Y? So can we predict someone's height based on their shoe size? X right here. X is called the explanatory. So this is X, this is Y. X is called the explanatory variable. Y is called the response variable. And we should use X's and Y's as generic variables. Y responds to X. So if someone walks in the room, if I have this data here, someone walks in and they wear size 10 shoe. Like, hey, what shoe size do you wear? Oh, size 10. Oh, I can predict how tall you'll be. Because if someone wears size 10, you think they're gonna be 30 inches tall? It's gonna be a baby, right? If someone wears size 6, are they gonna be 7 feet tall? Not necessarily. No, it's not gonna happen. Okay, so we can make predictions, and that's the idea of this. And this can be done with any two variables, like salt content in French fries, like sodium that causes high blood pressure, causes heart disease. And one killer of women in the United States is heart disease, heart attack, right? The salt, too much sodium. So if you're taking a lot of salt, is there a cause and effect, right? Does eating French fries, okay, the amount of French fries you consume, does that cause high blood pressure? Okay, see, and you can take a bunch of people, have them consume French fries. You can do an experiment. You can do an observational study. How much French fries have you consumed for the last 6 months? Let's look at your blood pressure. That'd be observational study. Okay, so that's the idea of explanatory and response variable and how they're related. So next, first thing we're going to do is scatter plot. We're going to create a scatter plot. So we can do this by hand. I need to make a nice vertical line. Let me get a better marker here. So this was from, if you recall, chapter 2, section 2. We created pie charts, scatter plots, or stem and leaf plots. We did histograms in 2.1. We did a bunch of graphical analysis. We made dot plots. Most of that was one variable data, and then all of a sudden scatter plots were up there. Okay, so sometimes scatter plots are taught, I've taught from other textbooks, scatter plots are taught in chapter like 2 or 3. They're taught in the beginning instead of all the way at the end. So some people can connect with this pretty easily. The X value goes on the X axis. Okay, this is 0 right here. Here's 0, and then I'm gonna put size 1 and 2 and 3 and 4. Why? I don't need to put all those numbers on there because we don't have any of that data. We don't have any size 1s or 2s or 3s. Okay, so I'm gonna start with the small shoe size. I'm gonna put a little break right here like we did with the histogram. I'm gonna do the same thing with height because we don't have anybody that's 0 inches tall because this spot right here is 0, 0. We don't have anyone that's 0, 0. So I'm gonna put a little break there. And the small shoe size looks like we got a 5. And we're going by half marks. So I'll put a half on there, 5.5. 6.5. And I'm trying to keep my scale. I don't think we had any size 11s. Again, the goal of all doing all this is make predictions, so I got my shoe size. I'm gonna label shoe size. And there's no units, but usually we put units on here. Like I wanna know, sodium content in hot dogs, right? Hot dogs have a lot of sodium. So this, the amount of sodium in hot dogs predict, the number of calories in a hot dog. So does X predict Y? Anyways, this is gonna be height. And it looks like we go 59. I'm just gonna go by ones. Do we have anybody that's 64.5 inches tall? No. I'm just gonna go whole numbers. 60, 1, 2. I usually have someone that's like 6'2" or something. But I don't have anyone there. Now I'm gonna put my dots on there. Just go one by one. Size 8. With a dot, go size 8 and 62. So again, this is why I didn't really need to write all of the data down on my paper. And in an actual problem, you'll be given that information. That's the given, right? So you want to go from there, off of this. I'm just gonna make my scatter plot here real quick, 9.5 and 67. If they double up, I usually put like two people have the same height and same shoe size. Let's put the dots like above and below each other. So you see they're like twins right there. 6.5 and 60. 9.5, 64, 10, 69, 6, 59, 6.5, 64. It doesn't have to be perfect. I mean, using a straight edge kind of helps a little bit. Okay. So I just created the scatter plot. And I want to describe what does it look like. Okay, so right here, we just have a bunch of numbers. Remember creating a histogram, and then we want to say, what does histogram look like? Well, what's the mean? What's standard deviation? Remember, we use the acronym SUCS. What's the shape? Skewed left, skewed right, symmetric. What's the outlier? That was unusual points. So where's the center, mean and median? Where's the spread? That was standard deviation. Okay, that was one variable. That's how you describe one variable data. Two variable data. We want to describe two variable data. And there's an acronym for this also, but I'm not gonna get into the acronym. We got too many acronyms. We're gonna describe. So we need to describe it using a couple of things. So we need strength. How strong is the relationship? Form. We need direction. And we need context. Strength, form, direction, context, not necessarily in that order. So we can write it just direct. Or you could write it as a sentence, and I'll do both, okay? I'll do both of those. So I'm gonna describe this data set right here. So this is there a correlation between shoe size and height? That's a yes, no question, isn't it? Is there a correlation? That's my question. It looks like there is a correlation. Like I said earlier, if somebody walks in wearing size 9, I could predict where they're going to be somewhere, probably right up in here somewhere, right? That's how tall they are. About. It's an estimate. If someone comes in wearing size 9, they're not gonna be 6 feet tall. That's way up here. So you can kind of see the positive direction going right there. Does everybody see that? Positive. The strength, how strong is it? So we have words, very strong, moderately strong, somewhat strong, not very strong. Or we say, we use the word correlation, there's strong correlation, not very strong correlation. Or we could use the words, there's no correlation. No correlation means those two variables are not related. That would just be dots all over the place. That makes sense? I'm just using this example all through chapter 9, and then I'm gonna go to the book and point out some things that are in the book, some of the examples that you'll see that will help reinforce some of these ideas. Okay, so the strength, I would say somewhat strong of relationship, somewhat. So that's the word. Somewhat strong. I can use the word weak. There's a weak relationship between two variables. And we'll get into this R value. This R value tells us how strong the relationship is. The form. Linear. With form, we could have linear or nonlinear. We could have a curved form, like an exponential growth. I don't know if you noticed, but if you go onto your calculator, when you went onto your calculator and you did one variable stats, there is linear regression, there's quadratic regression, there's exponential regression. There's all kinds of regressions we can do. We're only talking about stuff that's linear right now. The direction. There's no direction, or there's a positive direction or a negative direction. So in our case, we have a positive. Positive is going up from left to right, or increasing. If the dots were going down, an example of dots going down would be like years and world record time. So they had the track and field, like world championships this weekend, and like 5 world records got broken. They're like, there's either something wrong with the timer, or there's something, they had a tailwind. Why are all these records being broken? Records meant to be broken, right? So as years increase, world record decreases. So that's a way we can describe the direction. So the direction for positive, I'm just gonna write it down here. As X increases, Y increases. So we got, in our situation, we have positive correlation. If there's a negative correlation, as X increases, Y decreases. It's smaller. And you can imagine these dots doing the exact opposite. And I'll point out a couple of examples in the book. Again, if there's no correlation, the dots are just all over the place. Okay. The last one is context. What is the context that we're talking about? What are we talking about? Context means As shoe size increases, height increases. So there's a correlation between shoe size and height. Not X and Y. I'm not gonna put an X here and a Y there. I'm gonna write what X and Y are between shoe size and height. There's a positive correlation between shoe size and height. All right. Need to adjust my camera over here. Getting cut off my video. There we go. So as X increases, Y increases. X is shoe size, Y is height. So we're trying to make a prediction is, again, the ultimate goal. Does the explanatory variable predict the response variable? Does X predict Y? So if you have a bigger shoe, probably gonna be taller. That's what this means. That's what the picture tells us. If you just looked at the data, could you make that statement by looking at numbers? Remember, a lot of people are like, I don't know numbers. I don't know why I'm in a math class right now. I'm not even majoring in math or anything have to do with math. Okay, these are numbers. Most people don't understand numbers. But if I give you that graph, you're probably like, oh, okay, let's make a little bit of sense. I got a picture. Most people can understand pictures. Most people don't understand a bunch of numbers all over the place. It's a big mess, right? So we're making sense of the big mess. We're making a picture, then we're describing what the picture looks like by using that information. So here it is. Just write out the 4 things that describe the correlation. Or I can do it in a sentence format. I'm not gonna write a sentence because it would be a big, long sentence. I'm gonna use this information. There is somewhat of a strong, positive, linear relationship between shoe size and height. Does that make sense? Positive, strong, somewhat strong, positive, linear relationship between shoe size and height. Well, this is only based on the people in this class. What if I did this for a larger population? What if I did this with, what if we had a lot more males than females? Well, I probably have a little bit different picture, don't you think? If I would have a lot more dots, I have the dots everywhere. Well, I put a lot more dots on there. I'll have a lot more dots. I probably have more of a linear relationship. And I'll probably have people wearing size 12 and size 13. Well, let's guess where those dots would be. If somebody was in this class that wore size 12, how tall would they be? Probably about 6 feet tall, don't you think? Anybody know someone wears size 12? Are they about 6 feet tall? No, someone said no. So size 12, you're gonna be up there somewhere in that area. Not exactly. How about size 20 shoe? Okay, I'm thinking Shaquille O'Neal is like 7 feet tall, right? What's his shoe size? Like probably 20, like way out here?
24.
24, something like that. Yeah, some shoe like that. You got a specially made shoe, 7 feet tall. Okay, does that follow our correlation? Okay, or is that an outlier? Okay, outliers in correlations are not those points that are 20 and 7 feet tall. Because that dot way up there, there's Shaq. Follow the line. It's gonna be close to the line, don't you think? Okay, so that's not an outlier. An outlier would be, I think, probably this dot right here. Got a shoe that's 8.5 and 4'11", right? So probably an outlier. Somebody that has a larger shoe but is shorter. Or here's another outlier. Somebody that has a really small shoe that's really tall. Someone wears a size 6 shoe, 5'10". So those aren't not actually called outliers. In statistics, we call them influential points. So it's an unusual value. It's just influential in our correlation. So that's a scatter plot. Check. We create a scatter plot. We describe the scatter plot. Create and describe. What's next? What's our correlation coefficient? So all the R value does, it tells us the strength. R tells the strength of the relationship. And there's a big, long formula, and I'll point it out, like I said earlier. We'll go back into the book, we'll go page by page and look at where the R formula is at. You're all gonna laugh when you see it, because it's funny. We can find it on our calculator, thank goodness. So in order to find on a calculator, we're gonna have to enter this data into our calculator, and I saw a few people doing that already. So we're gonna enter, our X values are gonna be in list 1. And our Y values are gonna be in list 2. So let's take just a few minutes, just clear, do not delete list 1 and list 2. Let's clear list 1 and list 2. And enter these numbers. You may need a calculator. In the room.
Oh, yes, I do.
Okay. And after we enter the data into our calculator, what I'm gonna erase this so I have room in my board. So it looks like you should have 19 values in list 1 and list 2. It's kind of hard because you got to enter all of list 1 first. And then enter all list 2 first, but you got to make sure that they match up because the numbers go together. This is, each value is one person. That's the hard part about entering data for correlations. You may need more time with the numbers, double check. Okay, we're still right here on creating a scatter plot because we created it by hand. We could also create it on the calculator, which we have not done yet. So let's go ahead and do that. Remember the statistics plot, the stat plot function? We made histograms. We skipped the box plots. We didn't actually do box plots this semester. We didn't have enough time. But press second, y equals. And you're gonna get to a statistics plot. Turn plot 1 on. Make sure there are not 2 plots on. If you have 2 plots on, you're gonna get an error. So we have 1 plot with 2 variables. The very last graph, I believe, is a scatter plot with the dots. You're gonna look for the one with the dot. Is it the last one or the first one? I forget. First one, okay. So you're gonna look for the graph with the dots. That's a scatter plot. First graph. Press enter, and when you do that, all of a sudden it's gonna pop up X list and Y list. X list is list 1, Y list is list 2. I keep those the same. And it's gonna ask what kind of symbol do you want for your graph to be? Do you want dots? you want plus signs, that's just preference. I like the plus signs, it's a little bit different. And if we press graph, probably not gonna see anything, because your graph is gonna, your x-axis, we could change the window if we want what we see, but we have a quick shortcut. We're gonna press zoom stat. After you press zoom stat, does it look like that? No response, I guess.
Sorry, can you go back? I missed. And then when you do, second and one inches.
Yeah, so you're on stat plot. Yeah, so it says plot 1, plot 2, plot 3. You want to go to plot 1, press enter. And plot 1 is on or off? It's on. Okay, go to the first graph, which is the dots. Scatter plot. And all you have to do is from here is press zoom 9. Because it should have list 1 and list 2. So you're going to zoom 9. So with to make graph. Second y equals. And make sure you zoom stat, which is zoom 9. Does that explain why? Does shoe size explain the height? Okay, we want to know by looking at the graph, did that happen? Okay. So it should look something like that. There dots. Yeah, dots. X less than just 1. This one. Is it okay? We're good, we're there. So it might not look exactly like that, just because. You know, graphing by hand is not as accurate as graphing using technology. All right, so we described the graph. Now we want to come up with this value R, and like I mentioned, there's a complicated way to do this. With a calculation. I'm not gonna ask you that. I'm gonna ask you to do it on the calculator. So let's quit. Let's go to our home screen. So second mode, I believe. And we're gonna do another function. We're gonna press the stat button. We've been here 1,000 times. We were doing one variable statistics. This time we're gonna do a stat. And we're gonna do number 4. Is a lin reg. I believe it's number 4. You press stat.
Yeah.
Number 4. There's a number 8 also. So linear regression, there's a number 4, which is linear regression, and there's a number 8 that's linear regression. They are different. Okay. Here's why they're different. When you do linear regression, it's y equals mx plus b. That's what we learned starting in algebra 1 in junior high school. Y equals mx plus b, you learned it your whole life. Well, here, when you press number 4, it's y equals ax plus b. Did everybody see that? The AX plus B on there? Okay. Well, A, we're just replacing the slope of the line. This is slope. We're replacing the M with an A. Okay, but statisticians, for some reason, the back in ancient times or whatever, the statistics people didn't talk to the algebra people. So statistics people use the letter B to represent the slope of the line. So there's a number 4, which is this, and there's a number 8, which is y equals A plus bx. So statisticians use B as the slope. Algebra people, mathematicians use B as the y-intercept. Okay, I'm not going to confuse you because you've been doing this for most of your life. Y equals mx plus b. We're going to use ax plus b. A is the slope of the line. Slope. B is the y-intercept. X hasn't changed. X is shoe size and Y is height. The problem here is I'm gonna put a little symbol here. I'm gonna put a Y hat here. So in our case, in our context, I'm gonna define my variables. X is shoe size. And we got the new variable, Y with a hat on top, is not just height. Y hat is predicted height. So again, if somebody walks in the room with a size 9 shoe, I'm not gonna say, oh, 5'2" to 5'6". I'm not gonna say that. I want a prediction. I want to say, how tall is this person gonna be if they walk in with size 9? Oh, 65 inches, 5'5". That makes sense? Okay, so we're gonna predict. That's the ultimate goal, is make a prediction. So we're gonna use an equation to make a prediction. Shoe size and height. Okay. We need these variables though. We need an A and a B. Again, we could do it by hand. We could find A and B by hand. We can find R by hand, but we're gonna do it on the calculator. Okay. So you have to do something first before you can do it on the calculator. I'm not gonna trick you, but everybody needs to follow these steps. Press second and the negative sign, which is catalog. Does it say catalog on there?
Yeah, 0.
Oh, 0, second 0, thank you. Press second 0. You only have to do this once unless your calculator resets. Second 0. And you're gonna go to diagnostic on. So you're gonna go to the D's. Press enter. And enter until it says done. Okay, and this is silly why we have to do this, but some calculators don't have diagnostic on. If you don't have diagnostic on, your diagnostics are probably already turned on. So you don't even have to worry about doing that step. Don't even worry about it. It's not on. Okay. All right. That was a one-time thing for the people with old calculators. Yeah, don't worry about it. Yeah. Your calculator will probably be fine. You got a fancy one. All right. So now we're going to do the linear regression. What I'm trying to find the X, the Y, the A, and the B. I'm trying to find this number. Most importantly is R. So we're going to go back to stat, press the stat button. Go to number 4, lin reg A plus BX. Our X list is list 1. Our Y list is list 2. So X list 1, Y list is list 2. If you have stat wizard, you put X list equals list 1, Y list equals list 2. If you do not have stat wizard, if it just says lin reg A X plus B, you need to put an L1 comma L2. You don't do that if it asks for these two things. Okay, so there's kind of two different operations there depending on your calculator. I think that gray calculator, you have to put an L1 comma L2. Cause that doesn't have Stat Wizard. That's the silver edition. Need the platinum now. But now they're calling it Toyota. They have the silver edition, the limited edition, the platinum and titanium. Now they're calling it the capstone. They just gotta one up themselves, I guess. Kind of funny. Press enter when you're done. And a bunch of things should pop up. You should see X. Or I'm sorry, not X. It should be A, B, R squared, and R. Did everybody see those four things? If you did not see those four things, then you have to turn your diagnostics on. Because if it just says those two things, your diagnostics are off. For some reason, I don't know what. I gotta call Texas and let them know. Fix their calculators. Can someone read off the A and the B to me? Need a volunteer? Okay, volunteer.
A is 1.298.
I'm gonna put 1.3, okay, just make it easier.
B is 53. R squared is 0.44. And R is 0.66.
Okay. Did everybody verify that? Okay, if you didn't get it, you got different numbers. It's-
Almost, A 1.2, B 53.8, R 2.42, and then R 0.64.
That just means you entered numbers. If everyone agrees with this, if you're slightly off, then they just entered your numbers a little bit different. Okay, you just missed a number or something like that. If your numbers are way off, then go back and check your list 1 and list 2. You probably entered a 3-digit number or a single-digit number where you shouldn't have. Does that make sense? It's like if you put, this happens all the time, size 8, enter, size 9, enter. But you didn't press enter hard enough and it'll say 89. Someone's wearing a size 89 shoe. All right, so you gotta go check. Most important thing is entering data, right? So you double check your data, make sure it matches up with the book when you're doing a problem or a quiz or a test, stuff like that. Regardless, we're gonna focus on this number right here, this R number. I already gave you the name of R. R is called the correlation coefficient. R tells us the strength of the relationship. Okay, numbers close to 1 tells us there's a strong relationship. That'd be like a straight line. If all these dots were lined up in a row, there's a 1-to-1 relationship. That tells us it's a guarantee that shoe size and height are perfectly matched, but we know they're not. Okay, there's other factors, there's lurking variables that determine your shoe size and your height. One of them is gender, right? So your gender will determine your shoe size and your height. Your family background, right? So my grandpa wears size 7. My dad wears size 7. I guess I'm wearing size 7, you know? So there's a lot of other factors that factor in your shoe size and your height. Okay. So those things are all help us describe the data. But again, R close to 1, strong relationship, or -1. If there's a negative, this is a little less common. Like I said, world record data and year. Okay, does year predict our world record? Okay, we want to know, is there a correlation? In 1960, we'll use the 100-meter dash, for example. In the 100-meter dash in 1960 was like 11 seconds, right? Close to 11 seconds, 10.8 or something like that. Every year since 1960, 1970, it goes down a little bit. 1980, 1990, oh, we dropped down close to, all right, right around 10. Oh, then they start getting into the 9s, in the 2000s. They got these fancy track shoes and they got track suits now. And people are shaving their head because, you know, it makes you run faster. Okay, so now people, Usain Bolt, 9.65 or something like that. That's how fast he ran. Where in 1960, it was almost 11 seconds in 100-meter dash. Now it's below 10 seconds. Everyone's running below 10 seconds in the 100-meter dash. Okay, so that's a negative correlation. R tells us that relationship. So R is always the number correlation coefficient. Maybe I'll write it right over. Tells the strength. -1 is less than or equal to R, which is less than or equal to 1. Now, numbers close to 0 means there's no relationship. So I'm doing a correlation and I want to say, is there a relationship between these two variables? Okay, I got two variables. Is there a relationship between the number of hours of sleep you get per day and your GPA? Those are two quantitative variables, right? There's a correlation. So the hours of sleep and your grades. Is there a correlation? So if I do the math and I collect a bunch of data, put it on a scatter plot, I want to know, is there a relationship? And I find that there's a strong positive relationship. The correlation coefficient is 0.9. Well, I have evidence. That's some evidence. That's correlation, but not causation. Does sleep cause you to get lower grades or higher grades? Okay, the more sleep you get, the higher your grades. Doesn't necessarily mean that there's causation. Does that make sense? Your question earlier. It just means that there's a correlation. They're related. There could be other variables. There's other factors into determining GPA. Sleep could be one of them. Okay. Does that make sense? I hope. All right. So R close to 0. If there's R that's close to 0, like 0.12, 0.23, those numbers are close to 0. -0.3. Those numbers are close to 0. We would say there's not really a correlation between these two variables. The number of coyotes in the county and the number of wild rabbits in the county. It's funny, on social media, there was a pack of coyotes running down Blosser Road. I saw it on social media the other day. I'm like, pack of coyotes, I wonder, is that like 2 or 3? I'm thinking a pack, like 100, you know? School of fish. When I see a school of fish, there's like 20 fish or something. They said there's a pack of coyotes running down the street, etc. And is there a relationship between the number of coyotes and the number of rabbits? Okay. Oh, there's 0.2 correlation coefficient. Right? Does that mean all the coyotes are eating all the rabbits? Okay, not necessarily. So we're using this to make, if you're a biologist, that's something you would probably study. So that's R. Make sense? Again, we'll revisit all these things when we get into the book. Okay, next thing is our significance. We're going to look at the critical value, kind of like a p-value. We could find p-values by doing a linear regression t-test. That's something we're going to just bypass. We don't need to do a t-test. We don't need to find a p-value to say if there's a relationship. What we're going to do is find the critical value. So we're going to refer to a new table. After the table 4 and table 5, there's table 6, the chi-squared table, which we'll use. We're going back to the back of the book in Appendix A. And then there's the F distribution. We don't even learn about F distributions. We're going to look for table 11. I need some space. Go over here. I want to keep my scatter plot. I can erase all this up here. R critical value. R with a little c. R critical value. So this is table 11. There's no calculation. There's no calculator input for this. The critical values for the Pearson correlation coefficient. Notice there's table 10. There is a Spearman rank correlation coefficient, but we mostly use this more common Pearson. So notice there's N and then there's alpha. So we most of the time use the A26. We got N, so in our case, N equals 19, and most of the time alpha is about 0.05. So all I gotta do is go to n is 19 and now for 0.05, I got 0.456. For this problem right here, the R critical value is 0.456. That's a pretty low critical value. What we're gonna do is compare these two numbers, R and the R critical value. Let's compare them. That's telling me there's somewhat of a correlation, but it's telling me like a yes or no. Is that our correlation coefficient? Is it significant? So that would be a question. Is R significant? It's a yes, no. So that tells us again how related R is 0.66. The R critical value is 0.45. So any number above 0.45 is significant. Is R significant? If R is greater than R critical value, R is yes, significant. I don't need to write down the opposite of that. It's kind of like p-values, right? If p-value is below 0.05, then we reject. Well, the opposite is true. R is greater than 0.05, we probably reject. Yes,
What page is that on?
I'll go through all this in the book. I'm gonna go back through everything that we did today, where it's at in the book. Yeah. So, that's not actually in the book. It is kind of in an example, but it's kind of weird to find. But we're just looking at these numbers. This number is bigger than that number. Okay, 0.66, remember numbers close to 1 tell us there's a strong relationship. That means R is significant, right? That means there's a strong relationship. When a number, that's not a very strong relationship. If you got a small number like 0.3, that's not a very strong relationship. Well, 0.3 is below 0.45. R is not significant in that case. It just tells us, are they related? It's a yes, no. It's the way to answer yes or no. Just like with p-value, when you're doing a t-test or a z-test. Does that make sense? So that's the significance. Again, yeah, we'll go back through this whole entire thing, all right through the book where it's at in the book. Cool. Okay, check off correlation coefficient and R critical value. Check, check. We're right there. So we just focused on that R. And with any problem, your R is going to be a different number with every single problem. R is a calculation. A and B are also calculated. And again, we get into fancy ways to calculate A and B. But A goes here. A is the slope. B is the y-intercept. Does everybody see that? So we're just doing we're just plugging in. This is called substitution in math world. We're gonna substitute. You drink coffee with sugar, or you put a sugar substitute. You just replace the sugar with something else. Or you just do both. Sugar and sugar substitute. Put them all in there. All right. Let's write the equation of the regression line. So find the regression equation. It's the equation of the line. This LSRL thing I told you not to worry about. It's called the least squares regression line. That's not really that important, but if you ever see LSRL, that what I'm asking you to do is just find the equation. You want me to write it down? What I just said, or not worry about it? Don't worry about it. Okay. See people shaking their head. Least squares regression line. That's the statistical name of the line that we're going to draw. Really, like I mentioned, Shaquille O'Neal, size 22 shoe, 7'1". Where's the dot at? Well, if I drew a line on here, I imagined what my line would look like. Well, we can actually draw the line on there. I'm gonna draw a line that's gonna go right through all these dots. So I'm looking at the trend line, like the stock market. What's happening here? That line is called a regression line. If I find that line mathematically, it's called the least squares regression line. So RL regression line. I just drew a line on there, just where it might be. So that's one of the things that you might have to do. You might have to draw the least squares regression line. It's just also called the line of best fit. What does the line do? It allows us to make prediction. Shaq is up here somewhere. Nice 20 shoe. And he is 85 inches tall, I believe. 84 inches is 7 feet. 85 inches is 7 feet 1. I believe he's 7 feet 1 inches tall. Are you Googling it right now? Shaq's height? Oh, okay. All right. So you can see that the dots close to the line. Dots far away from the line are unusual. Okay, we don't want dots far away from the line. There's another thing that's in the books called the residual plot. The distance between the line and a point is called a residual line. Okay, I'm not going to focus on residuals. You may have heard of residuals, residue. Okay, they do this in forensics. There was a gunshot. There's gunshot residue on someone's hand, so we know that person fired the gun. They killed the person. You guys watch CSI or any of those series. That's all there was on TV for a while, where crime shows and emergency response shows, and they all copy each other. Anyways, forensics, they do that residue, residual. Okay, so that's the difference between the actual value. This is an actual value. All the dots are actual values. The number on the line, if you're on the line, that's called a predicted value. That's why we use this y hat as being the predicted height. Well, the equation on the line is going to be y hat. We're going to predict somebody's height from the shoe size. So we're trying to get the equation of the line. So here we are. A is 1.3. Here's the equation of the line. I just picked out the A and I picked out the B and I wrote it in an equation. I already defined the variables. That's something you need to do. You need to define your variable in context of the question. Write the equation. So what does that mean? What do these numbers mean? Okay. This is called the y-intercept. Remember the y-intercept? The B is the y-intercept. So when I kept going with this line, remember we had a little page break here. If I go to 0, if someone has size 0, 53 inches tall. That's what we predict. That doesn't make any sense. Y-intercept doesn't make any sense. Most of the time. Slope is really important. Remember rise over run is the slope of a line. We rise 1.3 over 1. What that mean? For every increase in one shoe size, I'm going to go up 1.3 inches. So as x increases by 1, y increases by 1.3 inches. So if I draw that on my line, I'm going to go over 1, up 1.3. Or yeah, 1.3. Go over 1, up 1.3. Go over 1, up 1.3. For that, the steps. Okay, that's what the meaning of the line is. So it's y over x. So if somebody's again shoe size 9, and they are 66 inches tall. So in size 10, we predict to be 67.3 inches tall, 1.3 inches taller. Okay, that's the meaning of the slope of the line. Again, I'm not testing you on slope, what it is. I'm testing you on, can you find the equation of the line? Let's predict. Let's make a prediction. Let's predict how tall somebody would be. I've been saying it. Somebody wears shoe size 9. If x is equals to 9, how tall are they? Or in fact, what is their predicted height? Okay, this is could be hard, could be really easy. I don't know your math background, but watch this. See that x is 9, so we're gonna go like this. We're gonna plug 9 where x is at. I don't have a calculator, but I think I can do it in my head. 9 times 1.3 is 11.7. Plus 53 is 64.7. Did you do that on your? You do that on a cell phone calculator. 1.3 times 9 plus 53. See 4.7, that's pretty close to 65. I'm saying 5'5". With this model, this is just a model, linear regression model. Someone where size 9, we predict will be about 65 inches tall. And I'm gonna put that on there. Where size 9, they're gonna be about 65 inches tall. My graph's a little bit off. I thought 66 when I used my graph to estimate that, but this is algebra, this is mathematics, right? Mathematics are better than just guessing. That's probably an underestimate. Size 9. Okay, we're thinking female shoe size about 1.5 shoe sizes off from male shoe size. There's a difference between those. So, I mean, we're talking shoe size, female wearing size 9. That's a rather large shoe, I suspect. About 5'5". Okay. I think 5'4" or 5'4.5" is like average female height, something like that. Average female shoe size. Probably down in here, probably like size 8. Something like that, right? So we're using this to make predictions. Using regression to make predictions. Again, that's 9.2, and I'll address that in a little bit. Make a prediction. And that's pretty much all of the 9.2. You're gonna just make predictions for different X and Y's. So I got A, I got B, I got R. This is R squared business. If R is 5, R squared is 25. If R is 10, R squared is 100. We just squared. If you square 0.66, it's weird. This is a smaller number. 0.66 squared is 0.44. The square root of 0.44 is 0.66. They're directly related. But there's a name for this R squared thing right here. Called the coefficient of determination. It determines this value, this R squared determines how well our line fits. The coefficient of determination, the line of best fit, how well does the line fit? Is the line a good fit? Does that predict Y, or are there other lurking variables? There could be a third variable. There could be a fourth variable that determines shoe size and height. Okay. We're just only saying is there cause and effect kind of with these two variables. Are we done with that right there? I kind of want to leave it up here for a few minutes just because you gotta do that. I'm going to focus on this R squared. I just don't have a space to focus on the R squared. R squared, coefficient of determination, numbers close to 1. R squared is always positive, first of all. If you have a negative R, if R is negative, negative number squared is positive. R squared is always positive, always a number between 0 and 1. Numbers close to 1 tells us really good fit. Numbers far away from 1 tells us not a very good fit. So R squared being 0.44 is the percent of variation of X and Y. Okay. And this is, I'm going to point out where this is at as well. I'll just write it down here. R squared equals blank percent of variation between X and Y. And we got this word explain. We can explain the variation between X and Y using this model. So I'm gonna use our question here. 0.44 is R squared. So that number as a percentage is 44% of the variation between shoe size, X is shoe size, and Y is height. 44% of the variation between shoe size and height are explained. So this is kind of a template between explaining R squared. So we can just use that template. There's a lot of examples that describe, and I think I only assigned 1 or 2 problems where you actually have to do R squared, but you have a quiz on it. There's a question on the quiz. Okay, one question. If 44% of the variation is explained, then that means 66% of the variation is unexplained. We write what percent of the variation is explained by the relationship between the two variables. Like I said, there could be a third and a fourth variable that explain the relationship between shoe size and height. So R squared is 40% is explained, 66, or I'm sorry, not 66, 56% is unexplained. So what's that add up to? That's 100% of your variation. So we have explained variation and unexplained variation. The very last thing you'll see is the standard deviation of the residuals. That's S. And S can be calculated on the calculator. Standard deviation. How spread out are these numbers around this line? The larger your standard deviation, the more spread these dots are. If there's large standard deviation, like in this problem, if I had dots that were like way out here, far away from that line, standard deviation is large. There's a large spread of the variation is very large. The dots are closer to the line. A smaller spread. Standard deviation is going to be much smaller. There's less spread in the variation of the residuals. Okay. And here's the way to find standard deviation of the residuals. Very last thing, I'll do it right over here. We can do a linear regression. Bless you, t-test. So we're t-testing. This is inferential statistics. And this actually pops up in chapter 1, even though I'm telling you now. A linear regression t-test also tells us, is there a significance? Is there a significant relationship between the two variables? If we get a small p-value, then yes. Strong relationship. If we get a large p-value, not a strong relationship. So our p-value is below 0.05. Let's do it. So we're going to do last calculation. Go to stat on your calculator. And this is a test. So we're going to go to test. Testing world. The last time we've been here. Have you guys seen that one before? Then red t-test when you go to testing. It's on there. You've seen it before and you always wondered what that was. Well, now you know. There's a ln-reg t interval as well. We're doing a t-test. Okay, so it's going to ask for all these funky things. Okay. B. Okay, that's A. Greek letter is alpha. Oh, alpha 0.05. Remember alpha? Well, what's B? B is beta. So it's going to say beta or this other Greek letter. Beta, is it equals, less than, or greater than? Okay. It's going to ask us, where's your X list and your Y list? It should generic or a default list 1 and list 2 should already be there, right? Did you already see that? So it just asks pretty much one question. All right, these two variables equal to each other. That would be equals and not equals if there's a horizontal line. Is there a negative relationship? That would be sloping down. Or is there a positive relationship? That's sloping up. This is positive. So this means negative. This means positive. So we're going to choose greater than. Okay, so choose greater than. And then calculate. I think I hit everything right there, right? Because all we had to do was choose greater than. It just asked us for one thing. And then we get all kinds of information. All kinds of stuff pops up on there. Okay, what pops up on there? Check this out. A pops up. B pops up. Don't you get an R and R squared on there as well? There's an S. There's a T. Oh, we get a T. What's T? T, numbers like close to 2, 3, 4. That means there's strong evidence. Oh, we get a p-value as well. You see the p? P-value. Somebody read to me the p-value.
9.51 with a scientific notation.
E negative what? E negative 4. 0.0009. Okay. What'd that tell us? Okay, small p value tells us there's a positive relationship. Small p value tells us a positive relationship. Large p values tells us there's not a relationship. That means there's not enough evidence that the slope is positive. Is that slope positive? There's strong evidence the slope is positive. That's kind of a t-test. Okay, I'm not assessing you on doing a t-test, but notice the lin-reg ax plus b and the lin-reg t-test kind of do the same thing, don't they? There's two ways to get there. There's two ways to get your a, your b, your r, and your r squared. That's the ultimate goal, is to get these four things.
The t-test is giving me y equals a plus bx, not ax.
Oh, okay, oh, good point. Oh, so they switched the two numbers.
Yeah.
So lin-reg t, good point. Lin-reg t-test does a plus bx.
Yeah.
Like I mentioned earlier, that's the statistical way. The b is considered the slope. So when you do a lin-reg t-test, they get b, this is the slope of the line.
Okay.
Yeah, so good point. So they swap those two numbers. Okay. I would prefer to do a lin-reg ax plus b. That's a little easier, right? The lin-reg t-test, that's just extra information. So again, finding standard deviation of the residuals, you might see that, finding S, that might pop up in a homework question. You might see something about residuals if you're reading the book. Okay, we'll get in other classes. I teach other statistics classes. Residuals, really important concept. It's other ways to measure if there's relationship. Okay, there we go. That's 9-1, 9-2, 9-3, and it's 7:05. So we're going to go through the book, and I'm going to point all these things out where they're at in the book. The book uses different examples and different information and kind of goes all over the place. I like this example because you can relate to it. Pretty good. Chapter 9. Oh, somebody mentioned this. What was that website again? How to use all the calculator stuff, because we've exhausted the calculator. It does more statistics than you ever thought. You remember the website?
I think it was scatology.
Scatology. Yeah. So scatology tells you how to enter your calculator stuff. But at the end of every chapter, there's all the stuff we've done on the calculator is at the end of every chapter. Chapter 7, chapter 8, and chapter 9, they tell you. It tells you the calculator stuff. Okay. Where are we at? 9.1, chapter 9, correlation and regression. Page 470. Definition: a correlation is a relationship between two variables. There, X is the independent or explanatory variable, Y is the dependent variable. Look at the graph at the bottom of page 470. Is there a positive relationship? Is there a negative relationship? Or is there no relationship? So there's pictures of it. Can everybody see that? Page 470? Yeah, pretty good explanation. Positive, negative, none. And I gave examples. An example of a nonlinear correlation where it looks like a quadratic, like a parabola. That would be like if you graph your speed and your miles per gallon. Anybody ever thought about this? Like how fast you drive, does that determine how much miles per gallon you get? The answer is yes. There could be a correlation up until a certain speed. So if you drive really slow, if you live in Los Angeles and you're in traffic jam every day, all day, they call it the 405 parking lot. Okay. If you're driving 10 miles per hour, you get low miles per gallon. What's the most peak miles per gallon? Is actually about 55 to 65 miles per hour. Okay, newer cars have like 10 speeds and stuff like that, and they're automatic. So you can actually go faster, lower the RPMs, and you maximize your miles per gallon. So it's somewhere between 55 to 65 miles per hour, depending on your car, make and model. Okay. Once you hit like 65 miles per hour, anything above that, you get lower, your miles per gallon start decreasing. So there's a maximum value. So it looks like a quadratic model. If you model your speed in miles per gallon, if you're going 75 miles per hour everywhere you go, your miles per gallon decrease. You know, this is really important to know in times like today. Oh, gas is $6 a gallon. And everyone's lined up at Costco to get gas to save 10 cents. Well, don't drive 65 miles per hour and you'll save 10 cents. Or I'm sorry, 75 miles per hour. If you don't drive 75 miles per hour, you'll save that money in gas. It was so funny. I was getting gas at Costco today. How ironic. And a Mustang, I was waiting in line. This old gentleman was getting in his car and he's getting his keys out. And there's a spot in the front, you know. And this guy's taking his time. And I was waiting for him to pull out. And I'm going to pull to the front. And this Mustang was behind me. Gets in front. The guy fills up and gets like, you know, $5 in gas. And he speeds off. And I'm like, there goes the $5. He just spit. He got gas really quick. I was like, what the guy wait in line? That's why he didn't want to wait in line. Probably was going to run out of gas. Anyways, that's the quadratic correlation. We don't do quadratic regression. Page 473. How do you calculate R? Look at the handy formula on R. Page 473. Go ahead and do it by hand. I encourage you to. N times sum of x times y minus sum of x times sum of y. If you actually look at it closely, you know what these symbols are. Sum, that just means add them up. Divided by the square root of n times sum of x squared minus, okay, blah, 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 blah. Anyways, you know what those variables are, but are you going to do it by hand? Probably not. Okay. Thank you, Texas, for making this calculator. There are several examples at the bottom of page 473. These are really cool. Perfect correlation, R equals 1. R equals 0.81. There's somewhat of a relationship, right? That was kind of like this. Somewhat of a strong, we said somewhat strong, remember that? That's the second graph right there. And then R equals 0.45. The dots are all spread out. So everybody see that? Page 473. Weak positive relationship. So there's words we can use to measure relationship. Oh, it's weak, 0.4. What if R is negative? -1, -0.9, -0.04. 0.04, that's like no relationship, no correlation. Make sense? Yeah. They tell you how to calculate R, page 474, all about calculating R. We skip all that mess. We can do it on the calculator. Page 476. Let's use the table to determine if R is related. So 476 and example 6 on page 477, talk about using the table. Is R significant? That's what we did right here. That's your R critical value using table 11, A26. And there's a couple examples there. Page 478. Write a hypothesis. I'm not testing you on writing a hypothesis because there's only one little thing about writing a hypothesis statement, but this is actually what we did. We did a lane reg t test. We did it all on the calculator, and that's what this is about. Find your t critical value. Well, if we did calculate t, it was probably like 3 or 4 or something like that. We found t. Why do we need to know t? Because then from t we can get a p value. They tell us how to calculate t by hand. Okay. You guys are not entertained. All right. Roger asked about correlation and causation. There's page 480. More information if I didn't explain it good enough. All in blue right there. Correlation and causation. What's the differences? What are the similarities? There they are. Cool. Yeah. Then we get into word problems. Page 482, 483. Age and blood pressure. As age increases, so does your blood pressure. Notice the blood pressure is higher in the 40s, 60s, and 70s. As you increase in age, you increase in blood pressure. Rite of passage, I guess. Age and vocabulary. As you increase in age, your vocabulary increases. Both positive relationships. Strength and sprint performance. Jump height, earnings and dividends, braking distances, drive surfaces. Okay, is there a correlation? So really all you're doing is finding R. In 9.1, I mentioned it. 9.1, scatter plot, correlation, find R critical value. Those are the most important things there. 9.2. A regression line is also called the line of best fit. Oh, I said that today. Oh, cool. There's a line for the sum of squares, the residuals is at a minimum. Okay. And the fancy name of it is y equals mx plus b, or least squares regression line, LSRL. So this is all about finding the equation of the line and making predictions. So go to page 491. In this case, practice makes perfect. Page problem 17, height and number of stories of a building. Okay, the taller a building, the more stories that building is going to be. If a building is 800 feet tall, how many stories will it be? If a building is 7, so there's the A, B, C, D. You see the A, B, C, D? Those are 4 different questions. So you do 800, 750, 400, 625. What are we doing with those X values? We're just plugging them into an equation. So you got to get the equation, and then you're going to plug those numbers in for part A, part B, part C, part D. So you're going to make a prediction for everything in 9.2. Cool? Pretty straightforward. Oh, hot dogs and sodium. I think I mentioned that. That's problem number 23. Hot dogs and sodium. Oh, problem 26. I mentioned this. Age and the number of hours you sleep. Registered nursing salaries. Is there a relationship? That's 9.2. Check, check. Finally, R squared. 9.3 is only about explained variation and unexplained variation. Bless you. Page 498. Explained variation, bottom of page 498, and unexplained variation. They give you some formulas there. We don't necessarily need to know the formulas. We just need to know what percent of the variation is explained and what percent of the variation is unexplained. So this kind of done in example 1 on page 499. The correlation coefficient for the gross domestic product of and carbon dioxide emissions is 0.91. Find the coefficient of determination. So if R is 0.91, in order to get R squared, we use squared. So we're going to do 0.912 squared. 0.832. What's 0.832? Interpretation. See the interpretation? 0.832 means 83% of the variation in carbon dioxide emissions can be explained by the relationship between GDP and carbon dioxide emissions. I kind of shortcutted that right here. You just say it's the relationship between X and Y. GDP and carbon dioxide. So the higher your GDP, your gross domestic product, I think they're talking about different countries of the world. Like you go to India, their GDP and the carbon dioxide emissions, right? Stuff like that. If you go to different countries around the world, you got different values. 16.8% of the variation is unexplained due to other factors. So there's other lurking variables that factor into why there's a relationship between the 2 variables. Again, there could be 3 variables or 4 variables. We don't get into determining that in this class. Finding S. I mentioned that on page 500, find your S, but you could do that by doing a linear regression t-test. I think there's one question where you're going to find the standard deviation of the residuals, which is not that important. It's chapter 9, and it's not even 7:30, and like I said. So try to spend like 20-30 minutes at least before you walk out the door today. I'm working on, starting 9.1. Got the data. Remember, clear your list. Do not delete. And you're gonna be like, oh, where'd this one go? Okay, so use the clear button when you're entering list 1 and list 2. Make sure your lists match up. That you got the same values in list 1 and list 2. And then do lin reg ax plus b, not a plus bx, and that'll get you your r, your a, your b, and your r squared. Cool. Some of the questions repeat from 9.1 to 9.2 and so on. So you can use them multiple times. I mentioned 9.4, we're not getting into it. Prediction variables and stuff like that, so you don't even have to worry about 9.4. Cool. Yeah,
What did you say we used to find the best?
S was the linear regression t-test, it was S. Now I gotta choose is these, one of those two things. All right. Here we go.